Thank you for coming. So I'm going to talk about hygroscopic growth of droplets within the human airway for drug delivery. I'm Mark Jermy. Most of this work has been done by Paul Stevenson, and we've been working throughout with Patrick Schoenemann of Fachhochschule Südwestfalen in Germany. And we'd like to thank Hauni Maschinenbau for funding this work, and particular thanks to Mark Kessler and Lasse Cornels. Just to briefly mention what hygroscopic growth is, if we have a droplet of pure water, it has a halo of vapour surrounding it, and the water vapour in this halo will be at the saturation vapour pressure of the water. And if the surrounding air also has water vapour at saturation vapour pressure, then this droplet won't grow. There's no concentration gradient which would cause water to diffuse to the droplet. So this droplet will stay the same size. Now, instead of pure water, if we have water plus dissolved compounds, those dissolved compounds are going to suppress the partial pressure of water in the halo immediately over the droplet surface. And because the partial pressure of water vapour in this halo is now lower than saturation vapour pressure, then if the surrounding vapour is at saturation pressure, then water molecules will diffuse to the droplet and the droplet will grow. That's hygroscopic growth. So this growth occurs when the surrounding gas has water at saturation vapour pressure at 100% relative humidity, and the water droplet has some dissolved compounds. So we're interested in drug delivery with evaporation condensation inhalers, and so these are inhalers for delivering various active compounds, which are very similar to e-cigarettes or vapes. The device that we were considering is not the one shown in this picture, but works on a similar principle. The user draws air through the device and it generates droplets of which are a mixture of water, glycerin, which we'll call VG, propylene glycol, which is called PG, plus some therapeutic or active ingredient. The droplets deposit in the user's airway, delivering the therapeutic ingredient, or they're exhaled again and lost. And we modelled such a device, which this orange curve shows the particle size distribution predicted by our model, which had reasonable agreement with laser diffraction measurements by Patrick Schoenemann. We're interested in the fate of droplets in the airway. The droplets are inhaled and some of them are deposited in the airway, and we want to maximise deposition in the deep lung because that optimises transfer of the therapeutic ingredient to the bloodstream. But hygroscopic growth occurs in the high humidity environment of the airway, and that's going to affect where the particles deposit. So we did some steady state modelling, and we used the Caresta puff profile. We actually just used the steady state part of this puff profile. So this is assuming that the user is drawing a constant 1.1 litres per minute through the device. The Caresta puff profile is a standard in the tobacco industry, and we used that because the kind of device we're looking at has similar resistance to a cigarette, and so users tend to draw roughly the same flow rate. So we put together a droplet growth model in which growth is driven by diffusion of vapour onto the droplets. This is a Stefan Fuchs or Maxwell model. There's one growth equation solved for each species. So this is the rate of change of mass of a particular species in the droplet. And it's a function of things like droplet radius, densities, diffusion coefficient, Sherwood number, and this function here where yi infinity is the mass fraction of this species in the vapour far from the droplet, and yis is the mass fraction of this species in the halo close to the droplet. And in this work, the species we consider are water, glycerin, which we'll call VG, and propylene glycol, which we'll call PG. We might also include a therapeutic ingredient, some drug which we want to deliver to the deep lung. But that's not done here because we wanted to keep this work generic. Droplet temperature is affected by the release of latent heat, conduction and radiation, and so droplet temperature can be calculated by solving this equation here. Latent heat is deposited into the droplet and the vapour simultaneously in proportion to their specific heats. And this model was implemented into ANSYS Fluent, a computational fluid dynamics package, using user-defined scalars, which are user-manipulable parameters set by code, which we integrate into ANSYS Fluent, and they compute the concentration of water, VG and PG in the vapour and in the droplets, and the droplet temperature. Now we implement this droplet growth model within a CFD simulation of flow in the airway, and the airway is a composite of four sections. First, a mouth-closed upper airway geometry. So that's this here. Here's the mouth, and then it goes on through the oral cavity, the larynx, and the beginning of the trachea. And this was generated from scans of a human airway, a 40-year-old male with no airway abnormalities. Nasal cavity was excluded, and it was meshed for CFD using an octree mesh in ANSYS ISIM. Then after that, we have the beginning of the lung model. So this is generation 0 to generation 7, and that was generated using the LungForcer program by Kitaoka and co-workers. And LungForcer is a piece of software for generating airway models, and there's a couple of studies which show that lung geometries generated with LungForcer have more accurate particle deposition rates than those generated from Weibull A airway models. So we use LungForcer to generate models of G0 to G7. We use a particular set of parameters, a particular set of settings within LungForcer. And then we use it to generate G7 to G15 with a different set of parameters. And then we generate G15 to G23 by taking the G7 to G15 model and scaling it down by a factor of 0.287. So together, these four parts of the model represent a typical adult lung at the beginning of inspiration, and it has a total lung volume of 6,388 milliliters. So here's the upper airway model. So the mesh in this model had 861,000 elements. Here's an image of part of the mesh, a slice through it, and you can see the structured mesh in the bulk of the airway and the inflation layers near the wall. Mesh convergence indicated this mesh would give about a 0.45% error in mean outlet velocity. We use species transport in the K-omega SSD turbulence model, although there isn't a lot of turbulence. Maximum Reynolds number is about 360. The output from the inhaler was initialized at the mouth, so this particle size distribution was used at the mouth. We used the Hans's Fluent discrete phase modeling module to track the droplets, and within that a user-defined function to set particle properties to those predicted by the droplet growth model. Stokes-Cunningham drag law with Brownian motion, Safman-Liff and thermophoretic force were enabled. The mouth inlet is a pressure inlet at 35 degrees C with a small water mass fraction that was determined by inhaler measurements. And the aerosol parameters, we initialized the droplets with 2.4% water, 65% propylene glycol, and the rest was glycerol. And the outlet was a mass flow outlet of 1.1 liters per minute, and the walls were set at 99.5% relative humidity, 37.5 degrees C. Here are some results from the upper airway. So here's a plot of the upper airway. The colored dots indicate where one of the track particles deposited on the wall, and the color of the dot indicates the size of that particle, its diameter at the time that it deposited. And in this model, 6.4% of the particles by number were deposited. So 6.4% are lost before the particles are drawn deeper into the lung. And the particles grow, so their growth ratio is 1.48. That means they're 1.48 times larger in diameter when they leave the upper airway as opposed to when they're first drawn in. And when they leave the upper airway, they have a water mass fraction of 59%, propylene glycol 26%, and the rest is glycerin. The particle size distribution and composition predicted at the outlet of the upper airway is used to set the inlet conditions for the next model. So here's the G0 to G7 model. Here's an image of part of the mesh. There were 7 million elements in this mesh, and that produced an error of 0.77% in mean outlet velocity. The extra boundary condition needed for that, for a model like this, is the pressure at each of these truncated branches, and this was set according to a set of data from a study by Pandal-Blanco and co-workers in 2019. So that's the blue curve on this plot here, and we fitted this yellow curve, an exponential function, to their data. Their data was at a flow rate of 10 liters per minute, and we scaled this down to 1.1 liter per minute. So this gives us the pressure at each outlet. This gives a maximum error of 49% between Pandal-Blanco's and the fitted results. That occurs at generation 3, but the error is less for later generations, and in reality interpersonal variations are likely to be larger than this modelling error, at least for the later generations. So the results from the generation 0 to generation 7 model were that 4.2% of particles by number were deposited in this region. And so here's a plot of where the particles were deposited, typically on the lower part of the geometry. The particles had a growth ratio of 1.67 times larger when they left this model than when they entered. And when they left, they had a water mass fraction of 72%. For generation 7 to generation 15, 5.4% of the particles by number were deposited in this region, and here's a plot of where they were deposited. Again, the dots are coloured by the diameter of the particle at the time it deposited. The particles had a growth ratio of 2.06, and by the time they left this model, the water mass fraction was 84%. Finally, in generation 15 to generation 23, 19.7% of the particles were deposited, so more of the particles are deposited in the deep lung, and the rest we assume are deposited in generation 23 or beyond. So that we count as the alveoli. What leaves this model is counted as deposition in the alveoli. Passing through generation 15 to 23, growth ratio is 2.87. By the time we leave this model, then we looked at increasing deposition in the alveoli by changing the particle size distribution. So in this graph, we see the blue curve is the original particle size distribution that we introduced at the mouth, and the orange one is one scaled up by 1.5 times. And the number of particles in each bin is scaled down to keep a constant total particle mass flow rate of 2.84 milligrams per second. We tried scaling up and down on size. And so this plot plots on the horizontal axis the mass mean diameter of the inlet particle size distribution. And on the vertical axis, we have the total particle mass, which is delivered to the alveoli. And it's a little bit noisy, but this has a peak indicating maximum delivery to the alveoli when the inlet mass mean diameter is about 0.8 microns. Then we tried increasing alveolar deposition by changing the initial water content of the droplets. And so on the horizontal axis here, we have the water mass fraction of the droplets when they first enter the mouth. And on the vertical axis, we have the rate at which Vg is delivered to the alveoli. We chose Vg as a tracer species because it's the least volatile of all the species. And we figured that any therapeutic compound would have low volatility and would deposit in proportion to the Vg. So when the Vg deposition is maximized, so is the therapeutic ingredient. So this showed peak Vg deposition in the alveoli with a water mass fraction something between 2 and 3%. So we could work out the dosage. So with the optimal size distribution and water content, a hypothetical therapeutic ingredient present at 5% by mass in the inhaled droplets would be deposited in the alveoli at a rate of 0.1 milligram per second of puff. So that means 70% of the initial content of therapeutic compound would be delivered to the alveoli. So in conclusion, hygroscopic growth and the deposition of particles can be modelled. Hygroscopic growth increases the mean size of the droplet and broadens the particle size distribution. The deposition rate at the alveoli can be optimized by controlling the initial particle size and the water content. Within the parameter range studied here, 70% of the therapeutic compound leaving the inhaler would be deposited in the alveoli if the size and water content are properly optimized. There are other studies of hygroscopic growth, but this study is unique due to its low flow rate. But it has some important limitations. The full breathing cycle wasn't modelled, and that means that Brownian deposition, particularly in the pause between inhalation and exhalation, isn't captured, and the loss on exhalation, breathing out particles, that isn't captured. And chest expansion and contraction were not modelled. Finally, here are the references which I've cited, and I invite you to ask me any questions.